Students, it is Friday, and this is your last lesson for the week. There will not be a test on this lesson, just like Wednesday and Thursday's notes, but there will be parts of this lesson that you will be finishing on your own that will be checked for accuracy. So that's basically where your graded assessment will come from this week. So before we get to the actual notes, I just wanted to illustrate something for you basically. When we talk about sets of numbers, numbers fit into different sets like counting numbers, integers, whole numbers. So just to kind of give you an example of what these sets of numbers look like, I want to just use like a real life example with you for a second. So let's say at Parkwood, there's this set of people called teachers that would fit into one group of people, for example. But within that set of teachers, you could have math teachers. Whoops. You could have math teachers. You could have English teachers. So, but they're not in the same group of subjects. They're not in the same subject, but they all fit in that group of teachers, right? But then over here, outside the teachers group, there's this other group of people in the school called students. So this group of teachers and this group of students, they don't intersect or anything. They don't overlap, so to speak. There are teachers and there are students, and nobody would fit into both of those categories. But within the teachers group, there could be English teachers, math teachers, social studies teachers, music teachers, all kinds of teachers that would all fit within this group of teachers. So numbers are the same way. You can have numbers in one set and not another. I don't even know if I'm going to be able to draw on here now. Let's see. Yeah, I can. Okay. You can also have numbers that are in one set or another. So when we talk about the set of real numbers, that's one set of numbers. So I'm going to draw another ellipse up here. So the set of real numbers could include irrational numbers. So we can have irrational and rational numbers, and those do not intertwine, they don't overlap, but they're both in the set of real numbers. So irrational and rational. And I'll talk to you about what both of those mean. We could also have integers, we could have whole numbers, counting numbers, whatever. There is one set of numbers that does not fit into the real number category. You know how when we do the domain and the range and everything, we say all real numbers. Real numbers include irrational numbers, rational numbers, but they do not include one set of numbers, and that is the set of imaginary numbers. And if you remember yesterday, we talked about imaginary numbers. The imaginary number, the way we kind of denote that, I guess you could say, is with a lowercase cursive I, and I equals the square root of -1. Okay, so then when we start to write, when we start to simplify our radicals or our square roots, we're going to sometimes have to use the I, the imaginary set of numbers. And believe it or not, yes, there are, when you have a parabola, for example, and you don't have to draw this or anything, but when you have a parabola, it's a quadratic. So it does have an x squared in it, okay? But if it's up here and you can't see where it crosses the x-axis, it still has two roots, but it has two imaginary roots. And I'm going to show you some today where it does end up being imaginary. I also want to talk to you about the set of irrational numbers, and we talked about this a little bit. I think last week I talked about it just a little bit. Rational numbers rational numbers can be expressed as can be expressed as a fraction. This includes repeating decimals, and what we call terminating decimals. In other words, that it does have an end. So even numbers like, let's see, like 0.4956, you can, even if it's repeating, okay, so you put that line over it, it's repeating, you can write that as a decimal. You would write 4956 over 9999. So that can be written as a decimal, okay? Irrational numbers, on the other hand, these numbers cannot be expressed as a fraction. In other words, you can't write them as a fraction. So and what we include in this is what we would call a non-terminating or non-repeating decimal. And let's talk about what those look like. Irrational numbers would include numbers like pi, which, you know, we write as 3.14, but it's actually 3.14 and it keeps going forever and it doesn't actually ever repeat itself. Another irrational number would be root 2, root 3, root 7, root 11, root 13. All these are prime numbers. They don't have other factors in them. So all of these are irrational numbers because they can't be, we can't write them as a fraction, and we can't simplify it anymore. So these are called irrational numbers. So we're going to be looking at basically 3 types of roots. We're going to look at rational, irrational, or imaginary, and we're also, yeah, so right here you see it says real, rational, or irrational. So the real roots are going to be either rational or irrational numbers. If they don't fit into any of that, if they've got that I in them, then they're imaginary. So we're just going to be, you know, kind of categorizing them in that way. So we're just going to like circle one of these. That's what we're going to do. All right. So, well, and you know what? What is rational? What is irrational? We already defined that up above. So let's just put a couple of, maybe a couple of examples. So rational would be 1/2, 3, -10, any of those. You could also have something like 0.45, and then that's repeating. So anything like that, that is a rational number. What is irrational? Pi, root 2, root 3. Those are irrational. And then, of course, imaginary is anything that has the I in it. Okay? All right. So remember, too, that we need to put the plus or minus on there when we do the square root. Okay. Okay, so let's look at number 1. This is, we're solving quadratic equations by taking the square root of both sides, or, well, we're getting the x by itself, and this is going to involve taking the square root of both sides. Okay, so on number 1, the x squared is by itself. That's the thing we want to do before we take the square root. And then we've got x squared equals 25. So to get the x squared, to make it an x, we need to take the square root of that. So we have to take the square root of both sides. So then when we take the x out of the radical, we need to make sure that we answer this as a positive or a negative 5. The square root of 25 is 5, but it could be a positive 5 or it could be a negative 5. Because if you think about it, 5 times itself is 25, but negative 5 times itself is also 25. So we have to answer it positive or negative 5. This is a real root. Actually, it's 2 roots, so it's x is 5 or x is negative 5. So it's both of those, but we just write it like that top one, just saves room. So this is a rational. It's rational, and it's two roots. We've got two roots that are both rational numbers, 5 and negative 5. Okay, let's look at the next one. This one we need to isolate the x squared. So we need to get this part by itself. To do that, though, we have to divide by 3 on both sides first. So x squared equals 27. Okay, so then we take the square root of both sides. So now let's see, x equals root plus or minus square root of 27. But we need to simplify the square root of 27. That equals the square root of 9 times the square root of 3. So that's 3 root 3. So we would want to write this, x equals plus or minus 3 times root 3. So this one is, it's two real roots. It's positive 3 root 3 and it's negative 3 root 3, but because it's got this root 3 in it, that makes it an irrational root. So this one is, or it's actually a pair of irrational roots. Okay, let's look at the next one. Okay, so I'm looking at this one and I notice that this is a difference of two squares, so I don't really need to add 1 to both sides or anything. I can factor this to solve it. The square root of 4x squared is 2x. And the square root of 1 is 1. And I would have a plus here and a minus here. And I don't know if you remember the trick or not, but we're going to take the opposite of this and we're going to put that over this. We could solve for, we could solve it. We could do 2x plus 1 equals 0 and solve. But it's really easier just to say, okay, it's negative 1/2 and then positive 1/2. Okay, those are rational. If it can be expressed as a fraction, it's a rational number. So these roots are rational. And you're not going to have like one of each or anything. Okay, let's try another one. Let's subtract 3 from both sides. M squared over 15 equals negative 5. Okay, so now what we need to do is multiply times 15 on both sides. No, not negative 15. Okay, and then those cancel. So then we have m squared equals negative, I don't even know what that is. I'm going to have to figure it out. I think it's 75, isn't it? Yeah, 75. Negative 75. Okay, so when I take the square root of both sides, I have square root of negative 75. I don't have enough room here. I wonder if that might work. So negative 75 under this radical, here's how I'm going to rewrite this. M equals plus or minus the square root of negative 1 times the square root of 25 goes into 75. That's a perfect square, and 25 times 3 is 75. So what I did was I broke up the 75 into 25 times 3. The reason I used 25 is because it's a perfect square. You remember the perfect squares. I'm not going to write all of them, but all the way up to 144, we talked about those. So I'm looking for one of these perfect squares that divides into that number. All right, but I also need to do the negative part of it. So the negative part of it is negative 1. So my final answer would be m equals plus or minus, I need to do this thing first, 5, and then this one, I root 3. All right, so these are not imaginary. Oh, yes, it is imaginary. I'm sorry. So these are imaginary roots. So this would be one of those things where it would be above the x-axis like that, where you couldn't actually see where it crosses the x-axis. All right, let's see. We'll do number 5 together, and then I might leave number 6 for you. Okay, so on this one, I have to take the square root first, because that's the last thing that was done. So 2y plus 3 equals plus or minus 7. So on this one, I would break this up into two different equations. One of them would be positive 7, and one of them would be negative 7. So I would take this 2y plus 3 out of the parentheses. 2y plus 3 equals positive 7. And then over here on this side, 2y plus 3 equals negative 7. All right, let's do the blue one. Add 3 to both sides. 2y equals 10. Divide by 2. Y equals 5. All right, and then this one, add 3 to both sides. I'm sorry, subtract 3 from both sides. Oh, this was wrong. I'm sorry. I added 3. Let's fix that. Okay, subtract 3. That's going to be 4. And then divide by 2. Y equals 2. And over here, I'm going to subtract 3. Oops, I'm going to get a red. And that is 2y equals negative 10. Divide by 2. Y equals negative 5. So my two roots are 2 and negative 5. And these are rational numbers. Okay, I think I'm going to leave number 6 for you to do. So I'll highlight that one. Okay, let's see, what else have we got? Let's do number 7. Actually, I think I'm going to do number 8. So I need to subtract 6. I'm trying to get that x by itself eventually. That's going to be negative 42, okay? Then I need to divide by 3. That is 14, I think. Okay, negative 14. Okay, it's at this point that I take the square root of both sides. So the square root gets rid of that square. 4x minus 2 equals, okay, so this is going to be, oh, there is no perfect square that will divide into 14, but I can rewrite it as square root of negative 1 times square root of 14. So I can rewrite it as I root 14, but I need to do a positive or negative. Always do the positive or negative when you take the square root. All right, so I'm going to run out of room here. That works for me. That way I can write a lot smaller. So let's add 2. Actually, no. I'm going to set this up as 2 different equations. Because once you get to this part right here, if you've got stuff over here on the left, you need to set this up as 2 different equations. So 4x minus 2 equals positive I root 14. And on the other side, 4x minus 2 equals negative I root 14. Okay. So I need to add 2. 4x equals 2 plus I root 14. And that's all you can do. You just write it like that. You can't combine it in any way. And then divide by 4. X equals, we'll just rewrite it just like it is, 2 plus I root 14 over 4. That's one of them. Okay, let's add 2 again. This time it's 2 minus I. And then we know we're going to divide by 4, so we can just divide by 4 right there. Okay, so that's one of them. And that's the other one. And they are imaginary. Okay, so because real and imaginary numbers are in 2 different sets, I can't answer, even though this has, a root 14 in it, I cannot answer that it's both irrational and imaginary. So the way this is kind of set up is weird, but it's either going to be real or imaginary. So it's either going to be this or this. It can't be both. So if it's rational or irrational, those fit in the real numbers. So it's either going to be this line or it's going to be this line. And if it's this top line, you'll decide whether it's rational or irrational. It's kind of weird the way this is set up. All right, let's look at another one. Actually, let me look at all of these again because I want to see if maybe I want to leave one for you to try. I don't want you to try 6. Let's do this. Let's mark out number 9. We won't do number 9. You can mark that one out. Maybe I'll come back to it later, but for now, I want you to try numbers 6 and 7. And if you need help with them, all you have to do is just text me or something. Okay. Let's go back to 300. Simplify the following rational expressions. All right, so we're used to just like looking at the radicals and simplifying those, but some of these might have some negatives in them. I don't know yet. I haven't really looked at all of them very carefully, but let's just look at A, for example. So I'm going to keep, whoops, I'm still on my highlighter. I'm going to keep the 10 and the 5 for right now, okay? And I need to break down that root 50, and I need to break it down into root 25 times root 2, because 25 times 2 equals 50. And then what I can do is rewrite this again as 10 plus 5 root 2 over 5. Now, the 10 plus 5, I can't add those together. They're not what we would consider like terms, because this is just like if you saw something like 10 plus 5x. Well, you can't add those together. They're not like terms. Neither are 10 plus 5, 10 and 5 root 2. However, because I have 3 numbers here that, that could all divide by a common factor, I can simplify this some. I can divide all of these numbers by 5. Again, that would be like if I had 10 plus 5n over 5. I could divide all of those by 5, like that. Okay, so when I do that, divide all of them by 5, that one cancels, that one cancels, that one becomes a 2. So then my answer is 2 plus root 2 over 1, which I don't really need the 1 because it's in the denominator. So my actual answer is going to be 2 plus root 2. Let's look at B. Okay, so this one's going to be imaginary because I can see I've got that negative under the radical. So let's break this down. Let's rewrite negative 2 plus, okay, and then we're going to change the root negative 12 to root negative 1 times root 4 times root 3. Okay, so then what can be taken out of the radical? And then my 4 is down there. So let's look. What can be taken out of the radical? This and this, okay? So we're going to be left with a root 3 in the numerator. I think I can write all this right here. Negative 2 plus. Okay, so this is I and this is 2. But I need to write the 2 and then the I because it's like a variable. 3. So the 2 is like the coefficient of I. And then I've got a 4. Okay, so here again, I've got 3 numbers that can all be divided by a common factor. All of these can be divided by 2. So I'm going to do that. I'm going to divide negative 2 divided by 2 is negative 1. That's going to be, it's just going to cancel. It's just a 1. And then this is a 2. Okay, so now what do I have? I've got negative 1 plus I root 3 over 2. And when we're doing quadratic formula on some of these, they're going to look like this. Okay. All right. So this video is probably going to go about 35-40 minutes today because I've spent too long on it, but I'm going to leave some of these for you to try. Let's see here. If I feel like it, I think you can do this one. Try this one. Let's see. I want you to try this one. This one, because you can take square root of 121, that's 11. And I think you could also do this one. All right, so I want you to do those. And then we're going to move on because we've done some simplifying radicals already. Let's see, let's move down here. Okay, so this is just quadratic formula right here. I want you to mark out G and H. We've already done quadratic formula to some extent, so I'm not going to do this part right here because we've already done it. We've done quadratic formula. Okay, so that's completing the square. Okay, so I think we can get through this in about 15 more minutes. And then you don't have a notes video today, so that'll work. Okay. Quadratic formula we've already done, but I just wanted to review it because we might have some on this time that would have imaginary numbers. Okay, so A is 3. B is 5. And C, actually it's going to be negative 6. I didn't rewrite it. 3x squared plus 5x minus 6 equals 0. You got to get it to that point first, so I should have done that. C is negative 6. All right, so quadratic formula. It is up here on your notes. We're just going to go ahead and start filling in. So x equals the opposite of b. The opposite of b is negative 5. I'll just do the right colors then. Negative 5. This thing is so crooked. Plus or minus the square root of, okay, b squared. B squared is 5 squared, which is 25. Okay. And then that's going to be minus, let's do parentheses, 4 times a, and I won't always do colors, but I think I want to do one with colors, times c, which is negative 6. Okay. All right, and all that is over 2 times a, which is 6. Okay, it's 2 times 3. All right, so let's do the math here. I'm not going to do colors from now on. X equals negative 5 plus or minus. Okay, so 4 times 3 times negative 6. That's going to be 12. 12 times 6. I'm so bad with this. 72. So it's going to be negative 72. So that is 25 minus negative 72. So that's plus positive 72. That's going to be 97. Did I do that right? Let me make sure. I think that's right. So this is square root of 97 over 6. I'm trying to think of anything that goes into 97. There's nothing. Just want to make sure I've done this one right. Yeah, I think that's the answer right there. So negative 5 plus or minus square root of 97 over 6. Unless, no, there's nothing that drives into 97. Okay, I just really can't figure out why they would even put a problem like this on here, but this is the answer right here. So this is an irrational root, or a set of irrational roots. So the two roots would actually be, since we have the plus or minus, they would be, and you don't have to write this part, x equals negative 5 plus root 97 over 6, and x equals negative 5 minus root 97 over 6. Okay. All right, maybe this one will be more interesting. Let's see, x squared, I need to add 6x on both sides and add 9 on both sides equals 0. So I'm actually looking at this one and I'm like, this is a perfect square trinomial. I don't really need to use quadratic formula on this one, but we will anyway. Okay, so a equals 1, b equals 6, c equals 9, x equals the opposite of b, which is negative 6, plus or minus square root of 6 squared, which is 36, minus 4 times a, 4 times 1, 4, times 9, 36. over 2. 2 times a. All right, so this is 0. So x equals 6 plus or minus 0 over 2. So that's going to be 6 over 2, which is 3. This is a double root because we could have factored this as x plus 3. Wait a minute. Oh, minus. Sorry, that's negative. X plus 3, x plus 3 equals 0. So x equals negative 3, and it would be twice. It shows up twice. But your answer is just x equals negative 3. So that's a real rational root. Oh, and we didn't. This one was irrational, and this one was rational. Okay, how many more of these do we have? Just 2 more. Okay. I'm going to do one, and then I want to leave the last one for you to try. Okay, so C, and then I'm going to leave D for you to try. So I need to rewrite this 6x squared, because I'm bringing this over here, plus 3x plus 4 equals 0. Okay, there's no greatest common factor or anything, so A equals 6, B equals 3, C equals 4. X equals the opposite of B, negative 3, plus or minus square root of 3 squared, which is 9, minus 4 times 6 is 24, times 4 is 96. And all of that is over 2a, which is 12. Okay. X equals 3 plus or minus, okay, 9 minus 96 is going to be, okay, so that's going to be a square root of negative 89 over 12. Okay, does anything go into 89? I'm going to go to my calculator and do this one. Y equals, I'm going to clear this, 89 divided by x, second graph, nothing. It's prime. Why are they putting so many prime numbers in these things? Okay, so yeah, so that's it right there. That was boring. Okay, so that's irrational. Let me look at this one real quick. This one you're going to set up 3x squared plus 5x minus 2 equals 0. A is 3, B is 5, C is negative 2. Let's go ahead and do this one. X equals the opposite of B is negative 5 plus or minus. B squared is 25 minus 4 times 3 is 12 times negative 2 is negative 24 over 2a, which is 6. All right, root 99 can be written root 9 times root 11, so that's 3 root 11. I'm sorry, these are boring. Negative 5 plus or minus 3 root 11 over 6. I don't know. I thought maybe we didn't get any imaginary, but a lot of times you will get imaginary roots, but we didn't get any unless I did something wrong. If y'all see something I did wrong, please let me know. Okay. These are completing the square, and we've already done some of this. Again, we did this last week. I just wanted to maybe review it with you a little bit. Factor each trinomial as a square of a binomial. Okay, so these are perfect square trinomials, I think, all of them. Okay, so let's take the -2 divided by 2. Actually, we don't even have to do that. This is going to be -1 times -1. Yep, this is x minus 1 squared. So if we just take the 2 and divide it by -2 divided by 2, so take the x term divided by 2. Got ahead of myself, -5. So that gives you the factor. 12 divided by 2, 6. So this one's x plus 6 squared. It's just telling us these are perfect square trinomials. Okay, so look at part B. What do I need to make C to make it a perfect square trinomial? So I take the 6, divide it by 2, and then square that number. So 6 divided by 2 is 3, squared is 9. So x squared plus 6x plus 9. Remember, we did this last week, so I'm not going to spend a lot of time on this. -8 divided by 2, and then square that. That's -4 squared, that's 16. X squared minus 8x plus 16. Okay, I want you to do 3. So I want you to do this one. Okay, I want you to mark this part out. I'll just do it with my highlighter. Mark that part out. And then this is another completing the square example. I don't know why it's at the bottom, but okay. Here's how we're going to do this. You can follow these steps if you want to. This is how we did it. We took the x squared minus 2x minus 3 equals 0, and we moved the constant over here. So we added 3 to both sides. X squared minus 2x equals 3. Then you take the x term, you divide it by 2, and then you square that number. -2 divided by 2 is -1. -1 times -1 is 1. Okay, so that's what I need to add to both sides. So add 1 to both sides. X squared minus 2x plus 1 equals 3 plus 1 is 4. Now I can write this as a perfect square, as a binomial squared. That's going to be x minus 1 squared equals 4. Take the square root of both sides. X minus 1 equals plus or minus 2. And that's it. And I think that's it. All right, so I did it in 37 minutes. And I only left you, there's 1. We did all those. 2, 3, 4, 5, 6, 7. 7 problems for you to do. And most of this, again, is a review of last week. We just we did the imaginary numbers, but I think you'll be okay with that. So do those 7 problems. They're going to be graded. And that's it for this week. No test, nothing to study for. Everything's done for this week. So have a good weekend.